Okay. Is it the screen is visible to all? Hello? The screen is visible to all?
Yes, sir.
Okay. So in the last lecture, we seen that what is the linear transformation. We started unit number 4. What is the linear transformation? Before going to the linear transformation, we seen that some definition of transformation. Okay. The transformation, mapping, okay, corresponds. These are all the words are equivalent. Suppose x and y are the two given set. There is a mapping for each x belongs to x corresponds to a unique element in y for some rule, and that rule is called as transformation of x onto y. Okay. Also, we see that what is the one function, what is onto function. Okay. What is into function? What is many one function? Okay. Onto and into mapping. Onto is nothing but what? The codomain of the function is equal to range of that function. Okay, what is into? The range set is subset of proper subset of codomain. Okay, so what is one? Each and every element of the domain A is corresponds to only one element with B. Okay, one to one correspondence. And many one correspondence means what? One or more than one element in A corresponds to a element in B. Okay. So how we are going to prove the one oneness? Take the images are equal if A is equal to B. Okay, if we take an f of A is equal to f of B, and if it is implies A is equal to B, then it is function is 1 1. Okay, and what is the main function? If f of A is equal to f of B, that implies A is not equal to B. Okay, here we see that what is the examples of one function and onto function. Okay, so today we will see what is the equal transformation or equal functions. The next definition is equal transformation or equal function. Equal transformation. Okay, or equal functions. When we say that the two functions or two transformations are equal. Okay, look at the definition. Suppose suppose f is the function or f is the mapping from the set A to set B. Okay, and the set G, sorry, function G is a mapping from the set A to set C. Okay, these are the three sets A, B, and C. These are the three sets. Here, the function f and g are the two functions such that the domain of that function must be equal. Okay, so here f and g are the two functions from A to B and A to C respectively. Okay, B maps. Okay, the mapping. Okay, f and g are said to be wait are said to be equal functions or equal mappings. Said to be equal. Okay, if and only if. What is the condition? F of A small okay is equal to G of A for all A belongs to the set capital A. Okay, if these two function maps each and every element of A, and f of A is equal to f of A, G of A, then that function f and G are said to be equal function or equal transformation. Okay. For equal transformation or for equal functions, we have to the domain of that function must be same. Okay, if suppose this is the function from B to C, then we cannot say that f of A is equal to G of A. Okay, where the input A belongs to what? your domain, but is the what domain is what? B. Okay, if you take B. So for the equal function, the domain of that function must be same. The domain of the function is what here? A. What is the domain of the function G is? Also A. Okay. So for equal function, f is the function from A to B and G is the function from A to C. F and G are said to be equal if and only if f of A is equal to G of A for all A belongs to A, capital A. And this relationship is expressed. This relationship is expressed. This relationship is expressed by writing f is equal to G. Okay, then we can write f is equal to G in case of equal maps. Okay, equal function or equal mapping or equal transformation. Okay, so in case of equal map, the domain of mapping, the domain of mapping must be same. Okay, underline this statement. This statement can be asked in your exam. Okay, the domain of the mapping must be same. Okay, any doubt up to here? Equal transformation. Now, the next definition is inverse map. What is the meaning of inverse mapping? Inverse map. Okay. Definition. Let capital small f be the function from x to y. Be a 1 1 map. 1 1 and onto map. Okay, 1 1 as well as onto map. Okay, here the only one element is corresponds to one element in y. Okay, each and every element of x is corresponds to each and every element of y here. Okay, by 1 to 1 correspondence. Okay, and onto means what? The range set of that function is must be equal to codomain. Okay, then with the 1 1 and onto map, then f inverse is the mapping from y to x defined by f inverse of small y is equal to x. Okay, here input is belongs to the set y. Okay, so each y belongs to capital Y. Implies and implied what we have f of x. This is the mapping of f of x is equal to y. And f inverse is the function from y to x. Okay, it's called the inverse map of f. The inverse map of the function f. Okay, now out up to here, inverse mapping, if f is the function from x to y, 1 1 and on 2, then f inverse is the mapping from y to x. Okay, all it does now. But necessary condition is what? The function must be 1 1 and on 2. If the function is not 1 1 and on 2, you cannot define the inverse function. Okay. Now the product of two functions. The product of transformation. The next definition is product of functions. Okay, now definition. let f is the function from A to B. Okay, and G is the function now, not A to C now. Yes, B to C. Okay, A is the function from F is the function from A to B, and G is the function from B to C. Be any two functions or any two transformation. Then we define a map G into F, or we can say that G composition F. Okay, from F is the function from A to B, and G is the function from A to B to C. So G composition F is the function from A to C now. Okay. The domain of the first function, the codomain of the first function is B, must be the domain of the second function in the product of two functions. ओके तर एखाद्या फंक्शनचा कोडोमेन हा दुसऱ्या फंक्शनचा काय हवा, डोमेन असायला हवा. या फंक्शनचा कोडोमेन हा दुसऱ्या फंक्शनचा काय डोमेन आहे. Then we can define G into F, or G composition F is the function from A to C by the formula which formula, G composition F. Apply this function on element X, then G into apply the first F now, F of X. Okay, for all X belongs to capital A. Okay, now look at here. This X belongs to what? A. Okay, you apply F function F, let F of X be the element of B. Okay, now this is the codomain of F, and F of X belongs to B. Now, okay, so here the B is there. So F of X belongs to B now. So the input is what? For the function G is F of X. Hence, the codomain of the first function must be the domain of second function. Okay, that's why the condition is here. So G dot F is of X is equal to G into F of X for all X belongs to A. Okay, so here G composition F, okay, it's called the composite map. Okay, or we can say that product map. Okay, product map of two functions. Which one? F and G. Okay, now look at the example. Example number 1. Okay, any doubt up to here? These are the three definitions are there. Okay, which one? One.
Sir, voice clear yet nahi.
Wait. Hello? Any doubt?
Voice clear ही ना झाला है. आवाज येत नाही सर नीट क्लिअर.
ओके वेट. आता येतोय आवाज? बाकीच्यांचा पण तोच प्रॉब्लेम आहे काय? तुम्हाला तुमचाच
क्लिअर नाही सर, अडकतोय आधीमध्ये.
सगळ्यांचाच प्रॉब्लेम हा. तर तुमचाच प्रॉब्लेम असेल तर तुमचं नेटवर्क व्यवस्थित नसेल बरं का. तुम्ही बाहेर येऊन जरा जिथे नेटवर्क असेल तिथे येऊन बसा. ओके. So these are the three definitions: inverse mapping, equal functions, inverse mapping, and product of two functions or product of functions. Okay, now look at the example. Let example number 1. Let the map F is the function from set of real number to set of real number R to R, and G is the also the function from R to R. Okay, now domain of the codomain of the first function must be the domain of the second one. Okay. Hmm. B given by. These are the two functions given by f of x is equal to sin x, and g is the mapping such that g is given by g of x is equal to x squared. Okay, then find g of f. Then find g composition f and f composition g also. Okay, now answer. Now look at this one. G composition f is the function from f is the function from R. Now, what is the output of R? It belongs to this R. Now, this is the domain of G. Okay, so F is G comma F. G composition F is the function from this R to this R. Okay, so G composition function, G composition F is the function from R to R. And also F composition G is also from R to R. Okay, what is the function domain of this one G? R. Codomain is this one R. Okay, now this R is also domain of this f function f. Okay, so f dot G or f composition G is also by function from R to R. Now G composition f of T. We have to find this one. G composition f of T is equal to first apply f on T. F of T. Okay, what is f of T? F of T is given by f of x given by sin x. So what is f of T? Sin T. So g of sin T. Okay, so what is g of x here? G of x is nothing but x squared. But we have to find g of sin T. So put instead of x here sin T. Okay, so we get sin T bracket square, which is equal to sin square, which sin square T. So this implies g of f of T is equal to what? Sin square T. Okay, now we have to find f composition G of T. Okay, now first apply G on T. So this is f composition in the bracket G of T. Okay, what is G of T? G of x is given by x squared. So G of T is T squared. So here f as it is, G of T is T squared. Instead of x, put T here. In the G of x is equal to x squared. Okay, so here we get f of T. But what is f of x? F of x is equal to sin x. So instead of x, put here T square now. We have to find f of T square. Okay, so here we get instead of T square, instead of x, we put, if we put T square, so here we get sin T square. Okay, sin T square, not sin square T. Okay, the whole sin T का square होता है, तेव्हा sin square T आणि इथे काय आहे sin T square. So this implies f composition G of T is equal to sin T square. Okay, so these are the G of T, G of f of T and f of G of T. Any doubt up to here? Any doubt up to here? Hello, am I audible? आवाज ऐकू येतोय का माझा?
Yes, sir.
Okay. Now we comes towards next point, linear transformation, the main point of our topic. What is the linear transformation? Linear transformation. Linear transformation. Okay. Now, definition. Okay. In the above examples or in above definitions, we've seen that all the uh, functions are on the set. Okay, A, B, R, all are the set. Now, in the linear transformation, we define a function on the vector space. Okay, that linear transformation is also called as vector space transformation or vector space homomorphism. Okay, this word is also called as vector space homomorphism. Okay, now look at the definition. Let capital V and capital U be the two vector spaces over the field over the same field F. Okay, the field on this vector space, both the vector spaces are same. V over F and U over F be the two vector spaces over the same field. Suppose that field is K. Okay, V over K and U over K. These are the two vector spaces. And any map, any function T from V over K to U over K is linear map. It's linear map if first condition. What is that first condition? T of U plus V is equal to T of U plus T of V. Okay, these are the small u and v. And second one, T of A into U is equal to A into T of U. Okay, where U and V belongs to capital V and A belongs to that field K. Okay, this A belongs to field K. And U and V are the two vectors from vector space V over K. Okay, these are the two conditions. If these two conditions satisfied by any map, then we can say that T is the linear transformation. Okay, or sometimes we can write, okay, if T is the linear transformation, combining these two conditions in one statement. T of AU plus BV, okay, small v, A into U plus B into V is equal to A into T of U plus B into T of V, where U and small v belongs to capital V and A and B belongs to capital K field. Okay, so combining these two conditions in one. If this condition satisfied by any map, then we can say that that transformation, that mapping is linear transformation, linear map. Okay, or vector space homomorphism. Okay, any doubt in this definition? Okay, any doubt up to here? Okay, so the first condition we called as a vector addition. पहिल्या कंडिशनला काय म्हणतोय आपण? Vector addition. And the second condition is scalar multiplication. Okay, so this is the scalar multiplication and this is the vector addition. Okay. Now, so in other words, write down. In other words, a map. Hmm. F. Suppose F is the mapping from V to U. It's called it's called a linear transformation. A linear transformation. If it preserving, it preserves the following two basics operation. Two basics operation on a vector space. Okay, which one? First one is vector addition, and second one is scalar multiplication. Okay, vector addition and scalar multiplication. Okay, any doubt up here? So we can say that T is linear transformation. Okay, these are the equivalent words. Linear transformations or linear mapping. Okay, the meaning of all these words are same. Linear mapping or vector space homomorphism. Vector space homomorphism or linear function. Okay. Now, example. We will see some examples. Which is given by F is the mapping from V to V. Okay, F is the mapping from V to V, capital V to V, given by F of small v. Okay, F of small v. This is the small v, which is equal to itself v. Okay, that is identity mapping. F of A is equal to A. Okay, some like that. So for all small v belongs to capital V. Okay, small v belongs to capital V. Then F is called linear transformation. Okay, that is the identity mapping must be a linear transformation. Is a linear transformation. Linear transformation, and it's called identity transformation. Okay, identity transformation, and it is denoted by I. Okay, the identity mapping or identity transformation is denoted by I. Okay, so identity transformation always a linear transformation. Okay, now the second one is second example. Let V over capital K. Okay, capital V over capital K be a vector space. Be a vector space. Then the map. Then the map. hmm, F is the function from capital V to capital V given by hmm, F of small v. Okay, F of small v is equal to 0 for all v belongs to capital V. It's also called it's called again a linear transformation. Linear transformation. Okay, so every element from the V, okay, small v belongs to capital V, it maps to zero element. Okay, it maps to zero element of what? Capital V. And this mapping is also called as linear transformation. And it's called zero transformation. Zero transformation. Okay, and it is denoted by 0. Okay, so here identity mapping is always linear mapping. Zero mapping or zero transformation is also linear transformation. Okay, any doubt up to here? काही डाऊट आहेत काय इथपर्यंत? धोत्रे, बिराजदार, राकेश, काय डाऊट तिथपर्यंत?
No, sir.
So identity mapping and zero mapping is always a linear transformation. Now the third one, example number third. Let capital V be the vector space of polynomials. Okay, vector space of polynomials in the variable over x. In the variable x. Okay, over the field R. Over the field capital R. Let the function f of x, okay, and g of x. These are the two elements. These are the two elements belongs to capital V over R. Okay, f of x with a polynomial, g of x with a polynomial belongs to V of R. Okay, what is V? V is the vector space of polynomials. म्हणजे तुमचा प्रत्येक एलिमेंट काय असेल? Polynomial. Such that f of x, the nature of f of x must be a naught plus a1x plus a2x square plus up to so on an x raised to n. Okay, these are the polynomials f of x. Okay, if it is arbitrary polynomial, so the nature of f of x like this: a naught plus a1x plus a2x square plus up to so on an x raised to n. Okay, now small one, sub part of this one 3. Let D be the mapping from V to V. Be a map. Be a map defined by d of, okay, the nature of V is f of x. So d of f of x is equal to d by dx of f of x. Okay, so we have to find the derivative of that function. What is d? D is the differential operator. Okay, what is here map? D is the differential operator here. Okay, d of this polynomial. So we have to find the d image of this polynomial. So find out its derivative. Okay, so d of f of x is equal to d by dx of f of x. Evidently, d is well-defined function. Well-defined function. Okay, d is well-defined. What we have to show that is d is linear transformation. If you have to show that d is the mapping is linear transformation, what is the first condition? T of a plus b is equal to t of a plus t of b. Okay, or t of u plus v is equal to t of u plus t of b. So here mapping t is not there. Here d is there. So we have to find d of u plus v is equal to. We have to show that d of u plus v is equal to d of u plus t of v. But what is u and v here? F of x and g of x. Okay. So by the first condition of the linear transformation, d of f of x plus g of x is equal to what, by the definition what we have, d by dx of f of x plus g of x. Okay, so which is equal to if you have to find the derivative of x, what is this one? D by dx of f of x plus d by dx of g of x. Others find the derivative. So this is equal to what is this one? D of f of x plus d of g of x. So here we get d of f of x plus g of x is equal to f of d of f of x plus d of g of x. Now the second condition. This one is the first condition. Okay. Okay. This is first condition, and second condition is for the linear transformation is d of a into f of x. Okay, a into u. Here u is what? Polynomial is there. So it is equal to d by dx of a into f of x. If you have to find this one, derivative of this one, so constant term take outside. So this one d by dx of f of x, which is equal to a into what is this one? D of f of x. So here we get d of a of f of x. D of a into f of x is equal to a into d of f of x. Okay, so this proves that capital D is linear transformation. Okay, and it's called the side identity of the mapping zero transformation. So here the D is called differential operator. Differential operator. Okay. Now, in the third example, second part now. Second one. Again, consider the map. Again, consider a map I from V to V. Okay. V is the vector space. I is the mapping. Given by given by I of What is the input here? Polynomial. So here I of f of x is equal to integration from 0 to t f of x. Okay, we define the mapping like this. I of f of x is equal to, now instead of derivative we define here the integration of that function from 0 to t. Now first, through the first condition of differential operator, sorry, linear transformation. What we have? I of, take any two element from capital V. Okay, suppose f of x and g of x. By the definition, this is 0 to t f of x plus, this is dx, no, dx is there, plus g of x dx. Okay, but by the definition of integration, this is 0 to t f of x dx plus 0 to t integration g of x dx. What is this one? I of f of x plus this one is I of g of x by the definition of given to us. So here we get I of f of x plus g of x is equal to I of f of x plus g of x for all f of x and g of x belongs to capital V. Okay, and the second condition is B part. I of a into f of x by the definition of mapping. This is 0 to t a into f of x, okay, into dx, which is equal to, okay, if you find, if you have to find the integration of this one, take the constant term outside the integration. So here a into 0 to t f of x dx. Okay, so which is equal to a into, what is this one? A of I of f of x. Okay, so this implies I of a into f of x is equal to a into f or I of f of x. Hence, this proves that I is a linear transformation. Linear transformation, and it's called derivative of the differential operator. Okay, differential transformation with the integration. Integral transformation. Okay, any doubt over here? So these are the three examples, okay, of linear transformation. Any doubt up to here? Hello.
No, sir.
Now one more example is there, last one, fourth one. Let capital V be the vector space. Let capital V be the vector space of all n cross 1 matrices. N cross 1 matrices over the field capital R. Okay, over the field capital R, and let capital U be the vector space of all m cross 1 matrices over capital R again. Okay, now define a mapping. Define a mapping F from V to U. Okay, n क्रॉस 1 म्हणजे कसा आहे तुमचा हा कॉलम वेक्टर. ओके, m क्रॉस 1 म्हणजे हा एकच कॉलम आहे तुमच्याकडे. रो किती आहेत? n रोज आहेत. तो असा उभा असणार तो कॉलम वेक्टर. ओके, नाउ डिफाइन अ मॅपिंग f फ्रॉम v to u such that f of x, okay, suppose that column vector is x, which is equal to a into x for all x belongs to v. Okay. Hmm. What is a here? So a where, write down where a is m cross n matrix, right, over the field R, and is fixed. So fix the matrix I for this map. Okay, now we have to first show that this f is the linear transformation. For this one, we have to show that again the two conditions. Which one? First one, f of, suppose x1 and x2 are the two column vectors, which is equal to, by the definition of f, what we have? A into, instead of x here, x1 plus x2. Okay, now multiply this a into inside, a into x1 plus a into x2, which is equal to, what is a of x1 is nothing but f of x1. What is a of x2? F of x2. Okay, so f of x2. So this implies f of x1 plus x2 is equal to f of x1 plus f of x2. And the second one, f of small a into x1. By the definition of f, we have a into small a into x1. Okay, now a is the constant term, so take outside. So this a into capital A into x1, which is equal to a into f of this one is x1. Okay, so here we get f of a of into x1 is equal to a into f of x1. Hence, f is linear transformation. Okay, any doubt up to so here? Any doubt up to here? Okay, so this is the
No,
definition of
sir.
linear transformation and some examples of linear transformation. Okay, in the next lecture, we will see what is the vector space homomorphism. Okay, vector space homomorphism, what is the null space, okay, what is the kernel of a linear transformation, and what is the range space of a linear transformation. Okay, these are the two definitions we will see in the next lecture. Okay, for today it is sufficient now. Any doubt up to here? If anyone who have doubt, they can ask.